Hello everyone, my name is Jialuo Chen, a PhD student at the Zhejiang University, China. I'm glad to be here to present our work about deep learning model copyright protection. Deep learning models have helped us solve many real-world problems and facilitate our lives. For example, when you see a plant you don't know, you can take a picture and use an app to identify what species it is. However, training such high-performance deep learning models is by no means trivial, which requires not only large-scale datasets, but also significant computational and expert resources. As a result, deep learning models have become one of the most valuable assets in modern artificial intelligence. Unauthorized duplication or reproduction of deep learning models can lead to copyright infringement and cause huge economic losses to model owners, calling for effective copyright protection techniques. Here, we consider a typical attack defense setting with two parties, the defender and the adversary. Here, the defender is the model owner who trains a deep learning model using private resources. The adversary attempts to steal a copy of this model, aiming to mimic its functionality while evading detection, and the defender hopes to recognize model copies, that is, model ownership verification. This process should be robust and efficient. We identify three common threats to deep learning model copyright: model fine-tuning, model pruning, and model extraction. For fine-tuning and pruning, the adversary has full knowledge of the victim model, including model architecture and parameters, while for extraction, the adversary can only query the victim model for predictions. To achieve this, the adversary first obtains an annotated dataset by querying the victim model for a set of auxiliary samples, then trains a copy of the victim model on this annotated dataset. A number of watermarking techniques have been proposed to protect the copyright of deep learning models. Similar to traditional multimedia watermarking, deep learning watermarking works in two steps: embedding and verification. In the embedding step, the owner embeds a secret watermark into the model during the training process. Depending on how much knowledge of the model is available in the verification step, existing watermarking methods can be broadly categorized into two classes: white box methods for the case when model parameters are available, and black box methods where only predictions of the model can be acquired. White box watermarking embeds a pre-designed signature, for example, a string of bits, into the parameter space of the model via certain regularization terms. The ownership could be claimed when the extracted signature from a suspect model is similar to that of the owner model. Black box watermarking usually leverages backdoor attacks to implant a watermark pattern into the owner model by training the model with a set of backdoor examples relabeled to a secret class. The ownership can then be claimed when the defender queries the suspect model for examples attached with the watermark trigger and receives the secret class as predictions. However, these methods still suffer from certain weaknesses. Arguably, the most concerning one is that they are invasive. That is, they need to tamper with the normal training procedure to embed watermark, which may compromise model utility or introduce new security threats into the model. Thus, in this work, we present DeepJudge, a testing framework that produces supporting evidence to determine whether a suspect model is a copy of a victim model. DeepJudge consists of three components. At the test case generation step, it selects a set of seeds from the input dataset and carefully generates a set of extreme test cases. Based on the test case generated, DeepJudge computes the distance scores defined by the testing matrix between the suspect and the victim models. The final judgment of whether the suspect model is a copy of the victim can be made via a thresholding and a voting mechanism. We first introduced the testing matrix for two different settings respectively, white box and black box. In the white box setting, DeepJudge has full access to the internals and the final probability vectors of the suspect model, while in the black box setting, DeepJudge can only query the suspect model to obtain the probability vectors or the predicted labels. We first introduce a metric at the property level. Model properties can be used to characterize the similarity between models, and we define the robustness distance, ROBD, to measure the difference in adversary robustness between two models. The motivation is that the robustness of a model is closely related to the decision boundary that the model learns through its unique optimization process and can be considered as a special fingerprint of the model. If the model has a smaller distance on this metric, it means that the more likely it is a stolen copy of the source model. Neuron-level metrics are suitable for white box testing scenarios where the internal layers output of the model is accessible. Intuitively, the output of each neuron in a model follows its own statistical distribution, and the neuron outputs in different models should vary. Motivated by this, DeepJudge uses the output status of neurons to capture the difference between two models and defines the following two neuron-level metrics: neuron output distance and neuron activation distance. LOD measures the average neuron output difference between two models over a given set of test cases, while NAD measures the difference in activation status, activated or not activated, between the neurons. The layer-wise metrics in DeepJudge take into account output values of the entire layer in deep learning model. Compared with neuron-level metrics, layer-level metrics provide a full-scale view of the intermediate layer output difference between two models. Jason-Shannon distance is a metric that measures the similarity of two probability distributions, and a small JSD value implies the two distributions are very similar. JSD is designed for the output layer specifically. To fully exercise the testing metrics defined above, we need to magnify the similarities between a positive suspect and the victim model, while minimizing the similarities of a negative suspect to the victim model. In DeepJudge, this is achieved by smart test case generation methods. Meanwhile, test case generation should respect the model accessibility in different defense settings, black box and white box. In the black box setting, we populated the test set using adversarial inputs generated by existing adversarial attack methods on the victim model. The left figure illustrates the rationale behind. Fine-tuned and pruned model copies are directly derived from the victim model, thus they share similar decision boundaries as the victim model. However, the negative suspect models are trained from scratch on different data or with different initializations, thus having minimum or no overlapping with the victim model's decision boundary. Although the extracted models by extraction attacks are trained from scratch by the adversary, but they will gradually mimic the decision boundary of the victim model. In the white box setting, the internals of the suspected model are accessible. Thus, a more fine-grained approach for test case generation becomes feasible. As shown in the figure, given a seed input and a specified layer, DeepJudge generates one test case for each neuron, and the corner case of the neuron's activation is our particular interest. The judgment mechanism of DeepJudge has two steps: thresholding and voting. The thresholding step determines a proper threshold for each testing metric based on the statistics. The voting step examines a suspected model against each metric and gives it a positive vote if its distance to the victim model is lower than the threshold of that metric. The lower measured metric value, the more likely the suspected model is a copy of the victim. Based on the voting results, we can get the answer for the question in our paper title: copyright, yes or no. We run the experiments on 3 image classification datasets and 1 audio recognition dataset. The models used for the 4 datasets are summarized in table, including 3 convolutional architectures and 1 recurrent neural network. Positive suspect models are derived from the victim models via fine-tuning, pruning, or extraction. These models are considered as stolen copies of the owner's victim model. DeepJudge should provide evidence for the victim to claim ownership. Negative suspect models are trained independently using different training data or different initializations. The negative suspect models serve as the control group to show that DeepJudge will not claim wrong ownership. As model fine-tuning and pruning steps are similar in processing the victim model, we discuss them here together. The results are presented separately for black box and white box setting. For the black box setting, For each metric, the values below the threshold, indicating copy, are above the threshold, indicating not copy, are highlighted in red and green respectively. As we can see, positive models are all marked by red and negatives are all marked by green. That means the final judgment made by DeepJudge are identical to the ground truths. The results of white box testing are similar to black box, and it is not surprising as white box testing can collect more fine-grained information from the suspect models. To better understand the power of DeepJudge, we combine the results for each suspect model into a single reader chart in this figure. We use the orange line for the positive suspect models and the blue line for the negatives. Each dimension of the reader chart corresponds to a similarity score given by one testing metric. The larger the value, the more similar the suspected model to the victim. Thus, the field area could be viewed as the accumulated supporting evidence by DeepJudge metrics for determining whether the suspected model is a stolen copy. Clearly, DeepJudge is able to accurately distinguish positive suspects from negative ones. Here, we compare DeepJudge with 3 copyright defense methods. In short, DeepJudge performs better in the black box setting and comparably in the white box setting against the model fine-tuning and pruning attacks, while not tampering with model training. Model extraction, also known as model stealing, is considered to be a more challenging threat to deep learning copyright. We consider model extraction with 2 different types of supporting data, auxiliary and synthetic. Compared to model fine-tuning and pruning, the average ROBD and GSD values on the extracted models are relatively larger, meaning that the decision boundaries of the extracted models are more different from that of the victim model. Nonetheless, the 2 metrics can still reveal the unique similarities, smaller values of the extracted models to the victim model. The better the extraction, that is, higher accuracy of the extracted model, the lower the 2 metric values. This indicates that the extracted model behaves more similarly to the victim as its decision boundary gradually approaching that of the victim. This is further validated in the bottom figure, which shows the evolution of the extraction process. We explore potential adaptive attacks to DeepJudge based on the adversary knowledge. In the first setting, the adversary has full knowledge of DeepJudge, including the testing metrics and the secret test cases. And adversary fine-tuning is considered, which mixes test case into clean data and fine-tunes the stolen model. In the second setting, the adversary only knows the testing metrics. 2 adaptive attacks are considered, blind adversary training targeting on black box testing, and a general transfer learning attack on white box testing. We find that DeepJudge are partially broken under these adaptive attacks. That is, some metric values of positive models are marked by green, but the final judgments are still correct. Moreover, DeepJudge can recover the performance with new test cases generated with different seeds. And lastly, we make a brief summary and discussion about our work. The core of DeepJudge is a family of multi-level testing metrics that characterize different aspects of similarities between models. Efficient and flexible test case generation methods are also developed to help boost the discriminating power of the testing metrics. As a generic testing framework, new testing metrics or test case generation methods can be incorporated into DeepJudge to help define future threats. Although watermarking requires changes to the victim model, it also provides functionalities beyond what testing can check, such as embedding the owner identity, for example, signature or logos, into the model. We anticipate a long-running arms race between the model owners and the adversaries, where both watermarking, fingerprinting, and testing techniques are essential for trained effective defense. That's all. Thanks for listening.
Okay, so we've got Jialuo on Zoom. Are there any questions?
Watermark. Oh, yeah, now.
Wait,
okay.
Jialuo, can you hear what's being said?
Yeah.
Can you hear me?
Yes, yes.
Okay, thank you for the presentation. So I was wondering your white box watermarking scheme. First of all, is it a watermark? Does it change the model or is it a fingerprint? so it doesn't change the model.
Can I beg your pardon?
Oh, of course, yeah. So your white box watermark, does it modify the model's weights?
White box watermarking would change the model parameters.
Okay, so you actually change it. So I was wondering for your watermark if you evaluated, because you look at the feature, the distribution of every neuron, right? So I was wondering if you evaluated a shuffling attack, because we know that neural networks are permutation invariant, and there's been recently research coming out showing that a lot of the white box watermarking schemes are not resistant or not robust against these feature shuffling attacks or feature permutation attacks. And I was just wondering if you evaluated those in your white box watermark.
No, we have not studied this.
Do you think?
But
okay.
and I should correct my answer before that our white box testing does not change the model parameters because it is because it's a passive protection techniques that we generate test case on the victim model and test the distance, while white box watermarking indeed changes the model parameters. And then you mentioned the neuron shuffle attack. Yes, it is a great challenges to existing white box watermarking, and I have noticed that recently there is some works about neuron shuffling that indeed neuron shuffling it's difficult to define for existing watermarking techniques since it's based on directly calculating the weight parameters, and we think I think there is a possibility a possible method to mitigate this problem, since we can based on the neuron output statistics, we can rank the neurons by its output distribution. And if the attacker shuffle the neurons, we could re-rank the neurons by their statistics before we extracted before the attack. That might be a possible way to, and we hope to do more studies about this problem. Yes.
Okay, thank you. Thank you.
Thank you, Jialuo. Are there any other questions? If there aren't, well, thanks so much, Jialuo. It was a great talk.
Thanks.